Okay, hello everyone. I'm Henkai from Penn State. Today I'm going to share the work about investigating executable stack issues in Linux systems. So the story of executable stack is quite related to an old security topic, code injection attack. But how old is it? From the timeline we can see it's pretty old. Back to 1988, Morse worm became the first code injection attack, infected more than 2,000 computers. So that's a huge number at that time. And in 1996, the stack smashing paper showed more technical details about the code injection attack. After that, we have seen lots of code injection attacks, but no worries, the defenses are quickly deployed, and all of them share the same design, make the stack not executable. So nowadays, we all believe that code injection is gone, okay, not a threat anymore. But today, I will show you there is still a chance to find executable stack in the wild. First, a little background about the code injection attack. It normally starts with a bug to allow attacker to insert any content on the stack. So the attacker can first place the shellcode on the stack and override the return address to the address of the shellcode. After return from a function call, the program will jump to execute the shellcode. We can see the code injection attack heavily relied on the executable stack, but nowadays the stack itself seems to be not executable anymore. This is because the defense called write-xor-execute, which allows every memory page to be writable or executable, but not both. So you use one bit of the page table entry to indicate the CPU how to set up the stack memory permission. Because the design is so simple and straightforward, so the overhead, as we can expect, is very low. So the defense is quickly deployed and enabled by default on modern computers. Although write-xor-execute is such a major mitigation, and maybe the most basic one, we surprisingly found that executable stacks still exist on modern computers, on modern popular programs, and some of them are even open sourced on GitHub. For example, Electron, VS Code, CockroachDB, and Zero Tier 1. So why this keeps happening? We investigated these cases, and we found that the main reason is related to assembly files. So all these programs include at least one assembly file that missing the section definition statement for the node GNU stack section. So if you miss this section, you will make the final stack executable. Because the issue is introduced by a bad assembly files, so we term this problem badass. So here is an example to demonstrate the badass issue. So we prepare a simple C code. The C code itself has nothing special but hunts the program. We compile and run the C code. And we check the stack permission. We can see the stack is readable, writable, but not executable. Then we prepare an empty assembly file. So the empty assembly file has no content and should make no functionality difference. But when we compile it into the program and run it again, we can see the stack is executable now. So from previous cases, developers frequently forget to add this important assembly code. This is interesting, but what's the root cause behind this phenomenon is actually more interesting to us. So we have two general assumptions. First, the developers pay too much attention to the functionality, but never pay attention to the security features. So this could be one reason. Another is that maybe the enforcement or the defense design itself is so complicated or hard to use. So that it makes many people to overlook it. And to verify, we first investigate whether security experts can avoid this badass issue. And we conduct an in-depth analysis on the enforcement. Now let's move to the investigation part. So the best way to investigate security experts is to check their code. Here, the security applications. So we designed 3 criteria to help us identify the most suitable ones for the investigation. First, the tool should use assembly code for some purpose, like improve the performance or enhancing the security. And the tool should interact with the binaries. like generating new binaries or modifying existing one. And it will be good if the tool is open sourced. So after search, we found that init reference monitor aligns with our expectation. They use assembly code for security instrumentation. They output hardened binaries. And they are widely open sourced. So if any the bad ass introduced during the security instrumentation or hardened binaries will have the executable stack. But what's the init reference monitor, or IRM for short? So maybe this term is not widely used today. Their concrete implementations are well known, like the control flow integrity, software-based fault isolation. The core idea is simple, is to inject some security checks to the program to enforce the security properties. So the IRM compiles the source code to assembly and try to inject the security checks. And sometimes the check is linked as the security runtime. So all these three steps could interact with the assembly files and may introduce the bad ass issue. And sometimes it could also work on the binary directly. So in total, we investigate 21 open source IRMs, including 9 binary writers, 8 CFI solutions, and 4 other isolation or debloating tools. For the 9 binary writers, 5 of them have the bad ass issue, and 3 fix this issue. So I want to emphasize here that all these tools and the following mentioned tools, they are excellent works, their ideas are solid and working. So the only problem is during their implementation, they miss this issue. And for the 8 CFI solutions, 4 has the bad ass issue, and 3 fix this issue after our report. And both the isolation methods have the bad ass issue, and 1 fix it after our report. Now we can say that even security experts, they may miss this directive. So we cannot simply blame the normal developers, right? And the root cause may come from the write-xor-execute itself. So we conduct an enforcement analysis to the write-xor-execute, and following the complete combination process from the combination, assembly, linking, process creation, and library loading. And we reveal that all these steps are related to the stack permission. So when creating the process, the kernel will check the program handler called pt-gnu stack of the main binary and set up the stack memory permission based on the flag. Similar checks also happens during the library loading. So as long as one shared library has this issue, the final process will have an executable stack. However, this pt-gnu stack is generated based on the node-gnu stack section, which we mentioned before. So as long as one object file has the section flag set to execute, it will make the final linked binary an executable flag. Also, as long as one object file misses this section for the compatibility purpose, the final linked program will also set the handler to execute. The assembler will check the assembly files for this directive and set up the section. So if this directive is missing, the section will not be generated. The compiler will always generate this directive. So, and in most cases, the flag is none, indicating no executable stack needed. We can see that the badass skips this combination stage, makes the necessary section missing in the object file, set the improper flag in the program handler, and finally make the stack executable. If the badass exists in the shared library, any program that loads this shared library will have an executable stack. Maybe you think this enforcement flow is complicated enough, but actually this is a simplified version due to the limited time. So more details can be found in our paper. We reveal that, write-xor-execute is indeed very complicated. It requires concerted collaborations. And the bad assembly files break the regular enforcement routine. So, and the shortage of the node-gnu stack section is the main root cause of the executable stack. So is there any similar cases or any other sections like this? Yes, we found another one called not GNU property. So this includes 4 entries. If you miss this section, you may disable the Intel CET IBT and the Intel CET shadow stack. And you may trigger the stack overflow issue. And you may have the writable read-only memory. So we have seen there are some mitigations recently, but it shows that it's not enough. So we suggest for the tool-tray developers, we should always disable the executable stack by default, and only enable them with some explicit combination option. And for the normal developers, we should always include this directive when using assembly. And for kernel and loader developers, it's better to ask the user for confirmation. We also investigate the stack permission on other operating systems. OpenBSD is the first one to implement the write-xor-execute, and set it as mandatory since 2016. On Windows, the stack is not executable by default, but you can enable it with some special assembly. And for macOS with Intel CPU, you can also not executable by default, but you can enable it with a linker option. And for the Apple Silicon, it's always not executable. So in summary, in this work, we defined a term called badass that can enable the stack executable. And we investigated 21 security applications and found 11 have the badass issue. And it shows that even security experts, they may miss this directive and have the badass issue. We also conducted an in-depth analysis of write-xor-execute enforcement and shows it leads the concerted collaborations, and the design itself is too short for developer to notice. And we open source our investigation. Thank you. I'm ready for questions.
So we have time for one quick question. Yeah, come to the microphone, please.
Hi, thank you for your presentation. I had a question, because if I understand properly, your solution is to change the default to have the stack non-executable.
Yeah.
And I was curious if you knew how many programs actually need the stack to be executable for them to function properly.
So this is a legacy optimization for there is a function called a nested function. So it's only supported by GCC, but in the modern computers, it seems that the programs that need there are limited or no programs that need the nested function. Even Clown doesn't support this function. Yeah.
Thank you very much.
Okay, let's thank the speaker again.